Okay, let's get started here. So again, one final reminder that we have an exam this Friday in 2 days. It will be at 7 o'clock. Okay, I've mentioned this multiple times. Closed book, closed notes, about 90 minutes. Okay. The other thing I want to say is, I hope all of you already started reviewing the material, but the general strategy to review all the material is focus on the slides and the notes. Okay. The entire exam is only going to focus on material that I've covered in class. Okay, so essentially all the slides and all of the course notes that others have taken for the lectures is what you really need to know. Okay, if you understand the slides and the notes, I think you should be fine on the test. There is other material we have provided for some of the chapters for additional readings. Feel free to go read it just so that you get a deeper understanding of it, but you're not going to be tested on that additional material. Okay, you don't have to worry about knowing some arcane details of a paper or anything like that. Okay, so the focus has to be what I've actually covered in the lectures, and that's what will be fair game for the test. Okay, and you're expected to understand the material. So you don't have a very superficial understanding. Try to understand the concepts and whatever discussion we had in class, in Q&A, and all of that, it was captured in the notes, etc. Okay, so if you do that, you should be good. Okay, any questions about the test before I start the lecture? Okay. Yes, please. Okay, so question is, there was a sample midterm. Is there an answer key? I would have provided it, but I can't find it. I will look for it. The TA made the answer key, but I'm trying to look for it. If I find it, I'll put it up. I mean, there is nothing that prevents me from doing that. It's just me looking for it on there. But if you have questions about specific things that were asked, feel free to ask on Piazza, and at least we'll answer those. Okay. So, but I'll look again. All right. Any other questions? Okay. So what we'll do today is distributed transactions. Again, this lecture is not on the midterm, but of course it will be part of the final exam material that you should know. Okay. So what I'll talk about is this notion of transactions, which you probably have heard of from database. If you touch databases, you heard of the word transactions. I'll talk about those, but here our focus is essentially transactional concepts when you have distributed systems, okay, multiple machines trying to work on something together. Then why do we need transactions in that context? Okay, how do we implement this notion of distributed transactions? And then we'll look at how do you allow these operations that perform transactions to have high performance, which is basically the problem of concurrency controls and locking that comes with it. Okay, so let's start with the basics. Okay, so let's start with an example here. Okay, then you can try to understand why you need transactions and what they are. Okay, so let's take, there are two clients. Let's say they're performing operations on a server application which has some database, but really the database is not important here. Just assume that these are two clients. They have, and this is actually a banking example where each client has an account. Or rather, not each client. These two client applications are trying to make operations on the same account. Okay, so essentially, what you will do is a sequence of reads and writes on bank balances of records. So here's what is going to happen. So what we are trying to do is essentially try to withdraw some money from an account and add some money to the account. Okay, so we have accounts A, which has $100, B has $200, C has $300. These are the two operations we want to perform. You want to transfer $4 from account A to account B, okay, and you want to transfer $3 from account A to account C to B. Okay, so essentially B is going to get $7 from the other two accounts. All right. So if you think about it, if you just look at this, right, so you will say, if you perform these operations, A's balance goes down to 96, B's balance goes down to 197, and C goes to 307 because you transferred $403. Okay, so that's what should happen. Now, let's say these clients are making requests and they could be going or RPCs or whatever. This is a distributed system, right? So the server which has the bank database is remote. So maybe these are happening at the ATM or something like that, and you are making these requests. So here is what could happen, right? So client 1 is going to read A. Okay, A balance is 4. That's basically time is actually from the top to the bottom. The y-axis is time. So you read balance of your decrement $4. Okay, so you update A to 96. Okay, and then maybe B's request. So this is still ongoing, but maybe because client 2 has sent the request at the same time on the server, maybe the other thread gets scheduled because there are maybe 2 threads that are making these updates. Okay, so 2 reads the balance there and decrements $3. Okay, so far everything is good. Right. So now client 1, that thread runs again. It's going to read B because now you have to transfer that money to B's balance. You say 200. Okay. And then maybe that thread essentially gets scheduled out and then the other one starts running. So it reads the balance and then you have read 200. In this case, you're going to increment it. Okay. So this becomes 203. And then you switch back to this thread. It's already read the balance. Okay, which is now outdated, but it's basically going to continue from that point on, and it's going to just update it, increment it by 4. Okay, so you overwrite the changes that were made by client 2. Okay, so this interleaving is going to give us an incorrect result because this is not what we should expect to happen. Okay, now the important thing to note, okay, is this database, or in this case, these 3 accounts, they are a shared structure. Because multiple clients are reading and writing to it at the same time. So you will say, let's get locks on this. Okay? So if you say, okay, I'm going to put a lock on object A, lock on object B, and lock on object C. So that means before I read or write, I certainly need to get a lock. And then after each operation, I release the lock. Let's say you do that. Okay? So here you are going to get a read lock, read it, release it, and get a write lock, read it, release it, and so on. If you do this fine-grained locks, nothing is going to change here in this operation because you are just taking a lock for each operation and releasing it. Okay, so the other operation will still continue in that fashion. Okay, only if you took a lock on that entire database will you actually allow only one client to work at any given time. But if you do fine-grained locking, this is not going to change this problem. You'll still have this race condition, and you will have one client overwrite some other client's work. Okay. Is that clear? Okay, so what this says is just adding locks to your code sometimes does not give you the property you want. If your application is working on multiple data items, you don't want to take locks on individual data items. You want some higher level consistency semantics on what operations are happening. Okay? Either you can do that by locking everything, in which case only one client can execute at any given time. Right? You could have taken a lock on the entire database, and either client 1 or client 2 would run first, it would do everything, and then the other client run. Then you get correct results. Okay, but that prevents anything else from executing while one client executes. That is going to significantly improve, or not improve, rather degrade performance. Okay? So what you want is some semantics that allow multiple clients to read and write, and yet you want the correctness guarantees of what should happen if we had kind of done this the right way. Okay? So that basically gives us this notion of a transaction. Okay? So transaction has a higher level mechanism for atomicity in distributed systems. Yes, question.
So I'm not sure how locking does not solve the problem. For instance, if I have a lock on each record individually, then when I acquire the lock on A, I have both the read and write lock. So
okay.
When C tries to get the lock, then so client 2 has the lock. When client 1 goes back and gets the lock for B, it has the individual record for B, so it will not be able to either client 2 will not be able to read and write, so it will not have the problem.
Okay, so question is being asked is if you actually locked the entire object and perform multiple operations before you release the lock, the problem cannot. Okay, that is not fine-grained locking. All I was saying is each operation here you see takes a lock and releases a lock. That's what you would normally do. Okay, you are thinking of database locking where you lock the whole record. Okay, we have not even gotten to that point on. I was simply saying, let's say you're just writing Python code, right? You want to read a variable. You say lock variable, read the value, release lock. Okay. Then you later on you want to update the variable. You say lock the variable. In this case, take a write lock, update it, release lock. If you do that kind of fine-grained locking, each operation here is protected by lock, not multiple operations. Right. So that will not solve the problem. Right. So I am saying if you do fine grain, that is what you normally do in your code. And all I was pointing out is doing that does not solve the problem. Of course, you have to get coarser grain lock, which is lock the database, lock the rows, which we haven't gotten to, etc. Okay? But the higher level concept you want to understand is this notion of a transaction, which provides this, it's a higher level mechanism that provides the notion of atomicity of processing. Okay, what does atomicity mean? Atomicity essentially means that you want to protect a set of operations and you want all or nothing property. Either all of those operations succeed or none of them succeed. You don't want some partial number of operations to succeed and others don't succeed. So in other words, anything that is protected by a transaction operates as if there's one atomic operation, even though there may be multiple statements in there. Okay? So it's almost like a critical section in a piece of code where you grab a lock and you have bunch of things that have write code for, and then you release the lock. So it's the same kind of concept, but now you're operating on data. It's not code that we're talking about. Okay, so that's the concept we want. Okay, and that of course is something that has originated in databases. Databases perform transactions, and they essentially have this atomicity property all the time. Okay, we want to study it from the perspective of the distributed system. Okay, so here is what you want to happen. Okay. So it should look like, okay, either client one went first and did all of its operations in one logical unit. So you read A, you change the balance of A, you read B, you change the balance of B. So it should look like all of those 4 operations happened as one atomic operation. And then client 2 went and did all of its operation. Okay. And they can do it in either order. The order doesn't matter, but we want all of those client operations to be protected by a transaction. Okay. Transaction essentially gives us this atomicity property, which means all 4 of them succeed or nothing happens, which means that none of those A and B records have changed. Okay, so that's called atomicity. Okay, so all of these transactions give us something called ACID properties. Those are very strong properties that databases give, but in many distributed systems, you don't have all of those ACID properties. That's an acronym. I'll talk about that as to what it means. So A in ACID stands for atomicity. That means all or nothing. Okay, I just spoke about what that means, saying all of these 4 operations succeed and they're protected by a lock, or nothing succeeds. Okay, so that's what you want to happen. Okay, consistency says that you take the state of the system or a database from one consistent state to another. So if you are in one state, then you say everything looks correct. If you perform a transaction on it, the transaction succeeds, you are now in another consistent state. And to know what is a consistent state, here is an example of an inconsistent state. You don't want this to happen. Okay, that's what we mean by if everything was right and you perform some operations, you don't want something to get overwritten and get into inconsistency. Okay, so you want the consistency property. Okay, you want something called isolation, which means that when a database transaction is operating, okay, you don't want its changes to be immediately visible. Okay, but once they are visible, then essentially it becomes visible to the whole world. Okay, so immediate effects are not visible to others. This is also called the serializable property. That means you want the transactions to operate as if they are operating sequentially, like here. Okay, even though they're operating in parallel, the end result looks like this happened. Right? So you want the transactions in this case, or the clients, to execute concurrently. Okay? But the end result always looks like they had actually, as if they were executing sequentially. Okay? So that allows you to reason, say, okay, this is correct, because if they operate in this order, I end up with this result. Okay? So that is called isolation or serializability, okay, which we'll talk about. And the last thing is called durability, because that's the D of the ACID property, which says that changes, once they are permanent, cannot be changed. Okay? So once a transaction succeeds, which means it commits, you can't undo it. But until it commits, you can actually undo all of its effects. You can roll back, as we will see, to a state where it looks like the transaction didn't even execute. Okay? So this is again some material from a database class, because you need to understand the basics of a transactions for us to understand what distributed transactions are. Any questions here before we move on to the next part of transaction? Okay. So typically the way transactions work is you just as in locks, you want to acquire a lock, have a critical section, release a lock. Same thing with a transaction. You have essentially a begin transaction and an end transaction statement that everything within the begin and the end executes as if it's one atomic set of instructions. Okay, so you will, and then you can of course have other things like abort transactions. That means undo whatever has happened since the begin. Okay, and here is now we will get into essentially databases and distributed transactions and so on. So here's an example of making an airline reservation. Okay, so the airline reservation, let's say you want to go from city A to city B, but there is not a direct flight from A to B. So you have to go through multiple hops. Okay, and the entire reservation will succeed if you get a seat on each of the hops. Okay, and you don't want to get seats on two of the legs, but not the third leg, because that's not going to work for the traveler. Okay, so it's either all of the legs have to get a seat or none of them. Okay, so this is a good reason to put this in a transaction where you will say, okay, first go and reserve. In this case, you are flying from New York to Delhi. So you say, okay, go get a reserve a seat on New York to the Paris flight. If that doesn't work, then abort the whole transaction, undo whatever you did with the reservation. Okay, then you say go to the next leg, go to Paris to Athens. Okay, if not, abort, and then you do the last. Okay, so and then you do an end, which means all three have to succeed. Okay, and if any of them doesn't succeed, that abort transaction undoes whatever has been done until that point. Okay, this is standard database, nothing distributed yet. Okay, questions? All right, so now let's talk about a distributed transaction. A distributed transaction gives you the same idea, but now you're operating on multiple independent databases or multiple entities that are not normally related. Okay. Here is an example of two types of these transactions that are now going to operate on multiple entities. The first one is, let's say again, this concept of I am going to make a reservation for a trip, but now I want to make an airline booking and a hotel booking. Okay. Normally you go to two different websites or do two separate bookings. Okay, you book your airline ticket and you book your hotel ticket, but assume that you wanted to do this logically as one booking, because if you get a hotel but not a flight or vice versa, you are not going on this trip, right? So you want to make essentially do both or neither. Okay, so the way you would do this is you would use what is called a nested transaction, where you have a begin transaction and an end transaction, but there are smaller transactions in them. Okay, so you will essentially say I do a transaction on the airline and I do a separate transaction on the hotel. This could be two different companies, so there are two different databases. In this case, it looks like a distributed system, but then you protect both with a transaction, because if either one fails, you want to undo the other. Okay, so that's called a nested transaction. So you have a begin and an end transaction inside a bigger begin and an end transaction. Okay, so this is again a standard database thing where you can take transactions and nest them. You still have the bigger transaction also gives you the same property of ACID, so you can roll back anything that has failed, and until the big transaction commits, nothing is fine. Okay, now that's nested. Now let's think about distributed transactions. So what does this mean? Okay, so where things get distributed is, let's say your database itself is no longer on one machine, because you have lots of data. Okay, so you might have multiple machines actually managing your data. Okay, as is shown here. Okay, so you have one machine which is shown by this disk, another machine that has this disk. So it has your partitioned the data. So your collection of data looks like your logical database in this case, which is this bigger disk. Okay, so now if you want to make a transaction on this logical database, so you are going to essentially have sub-transaction. This is no longer a nested transaction, because from the user's perspective, the whole thing is like one database. Right? So you are trying to make a booking, airline booking or something like that, but the data is partitioned across multiple machines. So essentially you have sub-transactions that occur that try to get something done on one machine, and then some more things get done on another machine. And then that gives you this concept of a transaction. So it is essentially the concept of a transaction operating in a distributed environment where more than one machine is present. Okay? Logically, it looks like the same thing. Okay, because from a user's perspective, that's one database. Okay, as opposed to a nested transaction where there are two. But internally, the data is not on one machine. Okay, so this is going to make things like locking hard. Okay, because remember, a lock is something that is present in single process on one machine. Now, this concept of a lock has to work across machines. And last time we talked about a distributed lock, a distributed synchronization. So those kinds of concepts have to be thought about as you think about how to do distributed transaction. Okay, is that clear? Any questions here? Yes, good.
Can it be the case that one transaction is successful in one database and it is not in the other?
Okay. Question is it possible that one transaction is successful in one database, but not in a mirror database? So first of all, when you say mirror, that means there are two copies of the database. This is not intended to show that there are two copies. Okay? You are just taking a database. Let's say your database has become too large to fit in one machine. So you can basically slice it into two. So the first part is on one machine, the second part is on another machine. So it's not that you are actually keeping two copies. You are talking about a replicated database. We are not talking about replication yet. We are only talking about distribution. Distribution means you split it and partition it. Okay. Any other questions? Okay. Replicated database also have transactions, but that's not what we are talking about. Okay. So how do we implement these things? Okay. So there are two basic ideas that are going to apply also to a distributed system environment. Okay. First one is called private workspaces. Okay. So what happens in a private workspace is every transaction is essentially going to get its own copy of the database. You're not going to make a real copy. You're going to take a snapshot, which is more efficient, as I talked about. But the way to think about it is multiple transactions are running on the database. You don't want them to overwrite each other. Okay, so you give them each of them a copy of their own database. Okay, for now, assume that you actually made a copy and you gave it to a transaction. Okay, and so that transaction can go and make changes to its copy. Okay, and when it commits, you take its updates and then you put it in the actual database. Okay, so that's how it's going to work. So this is called a private workspace idea, where each transaction gets a copy of the database, which is essentially all the files that are present. Okay. So you think of it as a real copy, but as we will see here, you got a virtual copy. Okay, and you can optimize essentially this copy by using copy on write. And remember, we talked about that some time ago, and this is an example of copy and write, and I'm going to show you this example in just a moment. But what is going to happen is you make changes to your copy, and if the transaction commits, you take all the updates and put it in the main database. The transaction does not commit, you just throw away your copy. Nothing has changed in the database yet. You are operating on your copy, not on the main database. So it's very easy to abort because you just throw away whatever changes you made in your copy. Okay? But if you want to commit, you take your updates to the database and you put it in the actual database. Okay? So that's how it's going to work. So here is an example. Okay? So this is a file. Okay? For now, let's assume the database is a single file. The file has 3 blocks numbered 0, 1, and 2. Okay, this is the index to the file, which says that block 0 is kept here, block 1 is here, block 2 is here, and so on. Okay, that's a standard file. So now, if you want to have a transaction, you're going to make a copy of the file. If you made a real copy, you would have 2 copies of block 0, 2 copies of block 1, 2 copies of block 2, because that was what a real copy is. Okay, but you're not going to do that. You're going to make a virtual copy, which is a snapshot. So what you will do is you will create another index, okay, and just keep pointers to the same blocks. Okay, so the underlying data is not replicated. You just have 2 index structures that are pointing to the same underlying data. Okay, but as far as the transaction is concerned, it looks like it has its own copy. Okay, so far, okay, until it makes any changes, nothing has to actually be copied. But let's say the transaction now makes an update and it actually changes block 0. Okay, once you change block 0, you cannot go override that block, because that would actually update the actual database, because that's data from the actual database. So this is where you're going to use copy on write, which means you'll make a copy when you write. But if you're not writing, you don't make a copy. So now you will see that the block 0 prime has appeared. That's a new version of block 0. The old data structure is still pointing to the old blocks. Okay, this is the copy that the transaction has. and that block 0 prime is now actually a new block that you created on the fly. So you made a copy of 0 and you updated it. Okay? Now let's say you actually add something to the database that creates a new block 3, which is not there in the original database. So you actually allocate a free block and then write 3 there, which is 3 prime. Okay? So you will see that the transaction is now seeing its own copy, but any data that has not changed is still pointing to the original database. Any data that it changes, it gets its own copy, real copy. Okay, so physical copies are only made when you update. Okay, this is called copy on write. A very standard technique in distributed and operating system. Okay, makes you gives you efficient writes. Okay, now let's say take the last step where the transaction. So now if the transaction were to abort, okay, you would just delete this copy. Okay, which means you're going to delete these 2 blocks. Okay, any blocks you wrote, you delete, and everything goes back to the old state. Okay, but if you want to commit, you see what blocks were changed, and you copy them to the actual database. So you will see now that block 0 has been updated to 0 prime in the original database, and 3 has gotten added. So now the database content look like 0, 1, 2, 3, where 0 and 3 are now pointing to the new copies. Okay, so that's your commit. And so that now makes that the changes have become visible to the actual database. Okay, so that's the private workspace model. Yes, question.
Transactions have taken the snapshot at the same time, but both of them independently change 0 itself, and while they're committing. So, for example, first the transaction 1 is committed, in the transaction 2 commits.
Right.
It won't have the same copy of the.
Okay, question. That's a good question that is being asked. And the question is as follows. Let's say there are 2 transactions running in concurrently. So each gets their own copy. Okay. So now there are 2 additional index structures pointing to the same blocks. But let's say both of them actually modify the same block 0. The first one commits, and then it essentially writes to the database. And then the second one, when it commits, it's going to override the changes. That's the question. So what I have not said is when the commit is successful and when you have to abort. It's not that whenever you are done, you just update the database. What you have to do is exactly the question you asked, which is to say, since the time I took my snapshot, did any other transaction modify the same data I modified? If the answer is yes, you have what's called a write-write conflict, because you say somebody else modified it. If I go and modify it, I'm going to override. So in this case, you should abort the transaction. Okay? So there are additional locks that we have not talked about here at all on tracking that you have to do. This is just a simple idea. But that condition, if it occurs, should cause the second transaction to actually abort. Okay. Any other questions? Okay. So here's the second way you will do this, which is not making this copy at all. This is called write-ahead logs. Okay. So in this case, what you're going to do is you are going to let the transactions make changes to the actual database, okay, as it's executing. Okay. But when you commit, you're going to see exactly the question that was asked. Is it safe to commit? Has any other transaction modified this data or has done anything to what I have done? If so, you're going to abort the transaction, but you have to roll back all of the updates you made. Okay? So you have to keep track as you make changes what the old copy was, and then you do for something called a rollback. Okay? In the rollback, you're going to undo whatever has been done. Okay? So this requires that your system, whether it's a distributed system or a database, keep something called an undo log. Okay? What an undo log is, every time you make a change, you say what was, so let's say you're just changing an array, just as an example rather than a real database. Let's say you change the ith element of the array. So in the undo log, you have to say, before I made the change, the ith element was this value. After I made the change, the ith element of the array is this value. So you are going to keep this log. And if you want to undo it, you just replay the log backwards and you are going to basically undo the operation, as we'll see in an example. So the idea here is you make changes in place, but if there is a conflict or the transaction decides to abort for any other reason, you can undo whatever has been done. Okay, this doesn't require you to make copies or anything like that, but it does require you to keep track of when there might be some conflict and when you have to update things. Okay, so commits have to be atomic, which means you should not have the write-write conflict problem that was mentioned. Okay, so here is an example of a log and a transaction. A trivial transaction. Okay, your database has only 2 entries, X and Y. Okay, two values stored in the database. We'll assume that when you start the database, the values are both 0. Okay. The transaction is basically some operations on X and Y. So you add 1 to X, add Y, 2 to Y, and then you say X is Y times Y and so on. Okay. So this is going to now, in the private workspace model, you would have made a copy of X and Y and made changes there and then copy things back if you want to commit. That's not what we are going to do here. We are going to make directly changes to the actual copies of X and Y that are stored on disk, but we are going to keep a log that keeps track of every change that is being made. Okay, so here you go and say X is equal to X plus 1. So in your undo log, you're going to say X has been modified. The old value was 0, new value is 1. Okay. Then you are going to say Y is Y plus 2. You add another entry to the undo log saying, okay, Y was 0, it became 2. Okay, then you basically go X is equal to Y times Y. So you say X was 1, and essentially now it's become 4. Okay, so all these entries appear in the undo log. Okay, so at this point, okay, you will see that X has become 4 and Y has become 2. Okay, in the database. But now if you want to commit, you are done. You do nothing. You basically say the changes are already there. So there's nothing to do. Okay, the transaction. So you essentially in the undo log, you just write commit was successful. Okay. But suppose you want to abort the transaction. Now you got to go from X is equal to 4 and Y is equal to 0 back to the 0, 0 state, because that is what it was before the transaction started. Okay. The way you will do this is you are going to essentially go through the log backwards and essentially replay the log. Okay. So you will say, okay, value of X is 4, change it to 1. So you'll go into the database and change that value to 1. Okay, then you will say value of Y is 2, change it to 0. So you'll go back and change it to 0. Then you'll go back and look at the first record, the value is 1, change it to 0. Okay, so you're just going backwards and undoing everything you did. And then once you played that log backwards, you're back to 0, 0. Okay, so that will mean you aborted the transaction. The state of the transaction is back to where it was before the transaction started. So it is as if nothing has happened. That is what we mean by all or nothing. Okay, is that clear? Yes, you have a question. What's the question? Okay, force logs on commit. Okay, so question is, what does force logs on commit mean? So essentially, that is what I meant, saying if you're going to commit here, you're going to just write an entry saying I'm done. I don't need to unplay, not unplay, undo the log. Okay, so you don't have to do anything to the log. Okay, yes.
Two transactions can be interlinked.
Yes. Okay. Question is, two transactions could be operating on both X and Y. Okay, so what happens when you are actually making these changes and other transaction overrides this change? Okay. There are two answers to this question. We have not talked about locking at all here. Okay. So this is not all that you have to do. You essentially have to get locks. Otherwise, you will have that problem that you just mentioned. Okay, that's one, and that is what we are going to look at. How do you do locking? Okay, so in this case, that second transaction, once X and Y have to be has modified, this transaction should be holding locks on X and Y, which prevents somebody else from modifying it to begin with. Okay, that's one approach. But we'll also see another approach, which is called optimistic concurrency control, where you don't use locks. Okay, you say, okay, let's take an optimistic view. Let's assume that transaction conflicts are rare, that most transactions are operating on different parts of the database. Maybe you are making a booking to go to one city. Somebody else is looking for some other ticket, which has no conflict at all. Why take locks and slow everything down? Let the transactions proceed, but we'll keep track of conflicts. And when there are conflicts, we kill all transactions that made the conflict. So in this case, you will say, if these two transactions are overwriting each other, abort both of them. Okay? So that is a scenario where you would not use locks. The example you gave where two transactions are both modifying X and Y at the same time will occur, but you got to detect that. And when time comes to commit, you say neither of these can commit because you have overwritten each other. So abort both. So now you are back to a clean state and then restart both. Okay, so hopefully you restart at different times and this will not occur. Okay, so you will either solve that problem through locks so that the problem doesn't occur, or you basically detect the problem after it occurs and you undo everything. Okay. Any other questions? Okay, so that is the write head log example. Either of these could be used in a distributed system as well. Okay, now with that background, let's look at this whole concept of, I said so far we've not talked about locking, but we got to actually think about it. Okay, so why do we need to think about all of these things? So you could say I simplify the problem and put one giant lock on my entire database. Okay, so only one transaction runs at any given time, right? So there is not going to be any conflict. Every transaction goes in sequence. So essentially, made everything go sequential. Okay? But if you do that, your performance is going to take a big hit. Okay? Think about an airline database. Thousands of people might be trying to make a reservation. If you're effectively making them stand in a queue and say each one goes one at a time, you press book the ticket, it may take 5 minutes before all the other transactions finish and you're just waiting there. That's not a good experience for the user. Okay? And neither is it good from a performance standpoint because your throughput has essentially gone down dramatically. Okay? So you want to allow multiple transactions to execute at the same time. Okay? That is what concurrency means. You want concurrent transactions in your system, yet you want all of those ACID properties. It should look like you are executing sequentially, even though you are executing concurrently. So the end result should look like exactly the example I gave. You took a giant lock and you just executed by yourself. There is nothing else executing. So you essentially modified the database and another transaction ran and so on, even though multiple transactions are executing and making changes at the same time. Okay, so you want the property of transactions executing sequentially, even though they're executing concurrently for higher performance. Okay. So techniques that allow you to do that are called concurrency control techniques because they should allow this to happen, but they should also ensure correctness properties, the ACID properties that we talked about. Okay. So that's why we need concurrency control. Okay, here is how you will do it in a database. In the next slide, I'll show how you can generalize this for a distributed system. Okay, so this is not a technique, but it's just showing you architecture where you have a transaction manager that's going to deal with the private workspace model and the write-head log model that we talked about. Okay, so that is implemented at this layer. But as you are touching data items, there's a scheduler that's actually going to take locks and release locks and so on. And you have to do it in a good way, as we will see. Okay, because if you do the fine-grained lock that I was talking about earlier, you'll have the same problem. Okay, so you have to essentially do something more than just taking a lock and releasing it immediately and so on. Okay, so there is a lock. Essentially, the scheduler is doing all the locking for whatever the transaction manager is executing, and then the data manager is simply making the changes, whether the changes are to the workspace or to the actual database. Okay, so that's the conceptual picture you should have in mind. Okay, there is something that's implementing this notion of a transaction using either the log concept or using the concept of a private workspace. But as you touch data items, you have to take locks, okay? So that you don't prevent, so that you prevent write-write conflicts and things of that sort. Okay? So in a distributed system, okay, the same concept is going to apply. Okay, because we remember I talked about distributed transaction. Your data is now split across multiple machines. Your transaction is operating on data that's spread across multiple machines. So you still have a transaction manager that's executing the transaction. The transaction touches some data on machine A, some on machine B, some on machine C, and so on. So you do need a lock manager or a scheduler that's going to take locks on whatever is being touched and so on. And the scheduler may actually have to cooperate, okay, because it might have to depend on what to block on and so on. So it's not that you just look at your data, but you might have to look at what has happened on other machines. Okay, so, but beyond that, it's the same concept. Okay, you still have to deal with locking, you still have to deal with transactions, and then reading and writing is just the trivial part. Okay, so let's now talk about actual techniques that will be implemented with these kinds of systems. Okay, before we do that, okay, so we will have to ask what is the property we want. I already alluded to this. Okay, what we want is this property called serializability. You want multiple transactions to execute in parallel. The end result should look like the transactions actually went one at a time. Okay? So any end result that gives us that sequential property is correct. That's our definition of correct. Okay? And here's an example that will tell us whether this is correct or not. So we have 3 transactions there that are shown on this slide. Okay, all 3 of them modify exactly one value in the database, which is X. Okay. And you will see that they basically, this is some odd transaction, this example from the book, but doesn't matter. The first one sets it to 1, the second one sets it to 2, the third one sets it to 3. That's what is happening. Okay. So then the question is, you let them run concurrently. Okay, so the instructions will get interleaved. Okay, because they will actually be running in concurrently, and any end result that is acceptable to us will look like they actually ran in some order. Okay, either they ran in the order 1, 2, 3, 1, 3, 2. If there is some order that you can find that end gives you that end result, then you say that's correct, because you don't control what order they will actually run. Okay? But any order, any sequential order that gives us an end result we see at the end of that 3 transaction executing, we'll say is acceptable, because it looks like they ran in a certain order. Okay, is that clear what I said? We'll see the example to make sure what is acceptable and what is not. But what we want is we'll let them run in parallel. You look at the end result and you say, can this end result be obtained if those transactions ran sequentially in some order? You find the order. If you find one order that gives you that output, you say that's fine. That's a sequential order. Okay. So let's look at an example. Okay. So this is schedule 1, which say the instructions actually executed in that order. Okay. So you basically, so those are 6 instructions there. You just mix them up. Okay. So you say you're doing 0, x is equal to x plus 1. Next is 0, x is equal to x plus 2, and so on. So at the end of this, you'll have x is equal to 3. Okay. And you can say, yes, that is a valid output, because you could have run them as A, B, C, and you would, if you ran them in that order, you will see that x is equal to 3 is the actual output. Okay. In fact, this is sequential execution. As you will see, this is transaction A executed first, transaction B executed next, and transaction C. So this is obviously going to be correct, but that's an example of a legal sequence. Okay. Here's another one, okay, which is also going to be legal. Okay. At the end of this, you'll see that this also, because this is resetting whatever has happened to 0, and then you do x is equal to x plus 3. This output is also going to be x is equal to x plus 3. So we are going to accept it. Okay. But in this case, the interleaving looks more odd, because you say, I execute the first instruction of A, first instruction of B, then I execute the second instruction of A, second instruction of B, then I execute the 2 instructions of C. So it's actually getting interleaved in this case. But we'll take it, because that output looks like it executed sequentially. Yeah. So that's also legal. Okay. Here's a third execution. Okay. So in this case, you basically do the 2 zeros, then you do x is equal to x plus 1, then you do x is equal to 0, then you do the last 2 statements of B and C. This gives x is equal to x plus 2, and then x is equal to x plus. This is going to give us x is equal to 5. Okay. There is no sequential execution of those 3 transactions that will actually give you x is equal to 5, because you can put them in any order. Okay, A, B, C, you pick whatever order. There is no sequence that gives us that. So we'll reject this, saying this cannot be valid. Okay, this is not a serial output of a serializable execution. Okay, so this will be illegal. Okay, either the system should not even let this happen, or if this is occurred, then you should roll back the transaction. Okay, one of these 2 things have to be true. Okay, is it clear what serializability means? Any questions here? Okay, so essentially what we are doing internally is to look for conflicts that occur. So essentially, there are 2 kinds of conflicts that will occur: a read-write conflict and a write-write conflict. A read-write conflict occurs when you read an outdated value of a variable and then update it based on that outdated value. Okay, that's called a read-write conflict. A write-write conflict occurs if you essentially do 2 writes and one overrides the other. Okay, essentially this is a write-write conflict because you essentially gotten some value that should never have occurred. Okay, so you want to avoid both of these conditions from actually occurring. Okay, this is not telling us how to do it. This is just telling us we want serializable execution. But the idea is the scheduler should get locks to ever prevent these types of conflicts from occurring to begin with, and ensure that you only have serializable execution. Okay, All right. So we'll look at 2 or 3 different methods to do this. Okay. First one is called optimistic concurrency control. I explained this a little bit already. Okay. So in this case, we just let the transactions run in whatever order they want to run. There is no locks that you get. Okay. But at the end of the execution, you are going to validate the changes. Okay. You are going to check whether there is either a read-write conflict or a write-write conflict. Okay. If one of those occurs, then all the transactions that are involved in the conflicts, all of them get aborted. Okay. But the idea is in optimistic concurrency control, as I said, you take an optimistic view saying the database is large. Typically, transactions work on different parts of the database, so they don't conflict because your transaction 1 may be operating on certain elements of the database. Transaction 2 is operating on completely different elements of the database. So they don't conflict to begin with. Okay? So if this is the case, locking is only adding burden because it's there's an overhead to grabbing a lock and releasing a lock that slows you down. Okay? So optimistic concurrency control says, let's not bother taking logs. Let's check post facto, does this cause a problem? If there's a problem, we will abort at that point. Most of the time, there will be no problem. So we just let the transactions commit and everything is fine. Okay. So that's the basic idea of optimistic concurrency control. As you can imagine, it works well with private workspaces. Okay, because you let each one make their changes. You let them commit. When you're committing, you see, was there a conflict? If so, you throw it away. Otherwise, you make the change. Okay, so it's very easy. And there were no locks in private workspaces, so you can just do that very easily. Okay? So the advantage here is this approach is going to be deadlock free. There can never be deadlocks in optimistic concurrency control. Okay? Is it clear why?
So there is no locks.
There are no locks, so you shouldn't have deadlocks, right? So yes, it's a trick question. Okay, so there's always deadlock free, maximum parallelism, because there is never any blocking. Again, there are no locks, so there is nothing you are going to block on every transaction. You just execute, okay, whenever it gets scheduled. Okay. Disadvantage is that you have to rerun everything if there is a conflict and the transaction aborts. But the worst part is the probability of a conflict goes up at higher loads, because higher loads mean there are more transactions executing in the system. The probability that 2 transactions touch the same piece of data goes up as there are more and more transactions concurrently. Okay? So at heavy loads, okay, you are going to have higher probability of conflict and abort, which means that the throughput actually will go down at high loads because you're running a lot of transactions, but they keep failing. So you rerun them, okay, and they fail again. Okay, so the actual good put, which is the throughput of transactions that are successful, goes down, even though you are actually running at high load and you're wasting cycles repeating the transaction. Okay? That's the main disadvantage of optimistic concurrency control. That at high load, the failure rate of transaction goes up because the probability of a conflict goes up. Okay? So simple idea, because you don't have to do much. Okay? But there is a problem at high loads. Your question, yes. Okay, that's a good question. Question is, if you have 2 transactions that conflicted, you abort them and you run them again, and they are going to conflict again. If they run at exactly the same time again, it will conflict. Okay? So you might want to randomize it in the scheduler or something like that. Otherwise, you will have that problem. Okay? Now, that is not mentioned as a or specified. I should say, shouldn't say mentioned. That's not specified in optimistic concur. That's an implementation detail as to how you do this. Maybe you add a random amount of sleep before you retry. And this is what you do in networking. When you send 2 packets and they collide in Ethernet, you are going to do what is called a random backoff. So you wait for a random amount of time and then retry. You don't retry immediately because obviously you're going to collide again. Right? So same thing will happen here. So there are ways to avoid that you have to use. Okay. So now we'll look at techniques that are not optimistic. They're called pessimistic concurrency control or just concurrency control. Okay, they are not actually called pessimistic. By definition, concurrency control takes a pessimistic view, saying transactions can conflict. So let's actually do something to prevent it from happening. Okay, this is the way you are going to do this, is to essentially use locks. Okay, I should mention one more thing. Because of this problem of conflicts being, the probability of conflict being higher at high loads, optimistic concurrency control is not used widely in real database. I shouldn't say real, but commercial database system. Okay, so there are lots of research papers and research versions of databases and systems that have been developed, but commercial systems don't use them. Okay? Because you don't want to sell a product that starts failing at high workload. You don't want that to happen. So they are not adopted in commercial system, even though there are many research systems that have looked at this problem. And most of the commercial systems actually take a locking based view, which means they take a more pessimistic view. Okay? So the standard approach that is used in these databases and can be also used in distributed system is called two-phase locks, or 2PL. So there is essentially a distributed version of it that looks very similar to the centralized version. So I'm going to only describe one. So essentially the idea is that whenever a transaction touches some data item, you want to start grabbing locks on that data item, and you want to keep that lock all the way till you finish. Okay? So if you touch data item X, you grab a lock on F. Then if you touch Y, you grab a lock on Y, and then you wait. Not wait, but you keep the lock until the transaction finishes, then you release the lock, which means once you touch the data item and you grab the lock, no other transaction can actually touch that data item. And conversely, if you are trying to grab a lock on Y and some other transaction is in the midst of modifying Y and holds the lock on Y, you have to wait for it to finish, because otherwise you may modify Y where somebody else already holds the lock. Okay, so it's a locking protocol which says whenever you touch some data item in the database, let's say they are records or they're rows or they're just data items XY, you want to keep getting the locks. Okay? And then once you have the lock, you don't want to release them until the end. Okay? You hold them so that only at commit time you release. Because if you release them in the middle, then you will have a problem where some other database can actually, not database, another transactions can grab a lock and there may be a conflict and so on. Okay? So that's what a two-phase locking protocol does. So you never release the lock until you finish the operation on X. And then there's another thing here, which is saying once you start releasing locks, you cannot acquire locks again. That's a constraint that you put. Okay, so this is why there are two phases here. One is called the growing phase, and I'll show you a picture here. Okay, so this is the transaction on time axis, single transaction. The growing phase, you keep acquiring locks. So the y-axis is the number of locks you acquire. Okay, so each time you touch a data item, you keep getting locks on it. Okay, and then you can either wait till the end to finish, but if you're done with X, means I'm not going to change X anymore, you can, in this transaction, you can release the lock right away because you're done. There's nothing else you can do. Okay? So, but once you start releasing locks, you cannot grab any additional lock. That's a constraint, because if you do that, it can cause other problems like deadlocks. Okay, so this is called the shrinking phase, where you can only start releasing locks. So you have to wait until you're done with touching a data item, at which point you can release, but you better make sure that there is nothing new that you want to touch after this point. Okay, so the simpler approach is to not have a shrinking phase, and you do what is called strict two-phase locking, which is you just grab locks and then at commit time you release them all together. That's the simplest thing. Okay, you keep getting locks, wait until the transaction finishes, you release them all at once. Okay, that is called strict two-phase locking or strict 2PL. But the more general version says, don't keep the locks until the end because something else may be blocked. So you can start releasing them if you're done with that data item. Okay, this can let some other transaction that is blocked start rather than waiting until the entire transaction is finished. Okay? But you have to do this carefully. Okay, you can essentially, you have to make sure you're done with a data item in that transaction before you release it and so on. Okay? So easier way to understand is the strict version, but you can do this as well. Okay, any questions on, yes? Where is the question is, where is this level of detail implemented? So I'll go to a few slides back. So all of this is implemented in the scheduler that is actually going to grab locks and release locks. Okay, essentially that is what we'll need to figure this out. Okay. Question is, lock acquisition and release happens in the transaction. Shouldn't it be the responsibility of the transaction? That's the question, right? So this is the entire system that is implementing concurrency control. Okay. So how is the transaction going to work? You take some code and you hand it to the database. It will start executing it. And then essentially the transaction manager will see the begin transaction. It will start looking at or not looking, but start executing the code. As it executes the code, it tells the scheduler, go get a lock. So this is essentially the transaction manager is telling the scheduler to grab the locks, not that the scheduler is grabbing the lock by itself. Right? So still being done at that level, you see that it's being told to grab a lock based on whatever operations are being performed. Okay. So what you said is true. So maybe I should have modified my answer to say the transaction manager is executing the transaction and it works with the scheduler to grab locks. I think that's the right way to think. Okay, any other questions here about two-phase locking? Okay. So we will, in a couple, maybe 2 or 3 lectures from now, we will see another concept called two-phase commit, okay, which is called 2PC. It's completely different concept from two-phase locking. They sound like the same thing. Okay, both of them are 2 phases, but they actually have nothing to do with one another. Two-phase commit is a way to decide whether the transaction actually should commit or not, whether there was any write-write conflict and so on. Okay, so it's still a transactional concept, but it's completely different from two-phase locking, which is just saying, this is the order in which I grab locks and release locks. Okay? It's a little unfortunate that these two concepts have very similar sounding name, but they are actually different concepts. Okay, when we come to two-phase commit, I'll remind again that this has nothing to do with two-phase lock, even though it sounds similar. Okay. All right, so that is two-phase locking. We'll talk about one more thing and then we will end. So last thing is to do this concurrency control using the notion of timestamps, or in particular, Lamport's clocks or logical clocks. Okay, we talked about logical clocks several lectures ago. We said it is an integer that keeps track of events that are occurring in a system. And then as processes communicate, you essentially use this event to get the happened before relationship, where you can reason about 2 events and in what order they happen. Okay, so you essentially have logical timestamps that allow you to reason about in what order something is happening. Okay, so we can use that to decide whenever there is a write-write conflict or a read-write conflict, which transaction to abort. Okay, so normally if 2 transactions go and overwrite data that either of them is touching, so you have to at least kill one. Okay, you could of course abort both. But you don't have to do both. You can just say, I undo one and the other one succeeds. Okay, I just undo the operations of one, the other one succeeds. The question is, when there are 2 transactions that are conflicting, which one should succeed and which one should be aborted? Okay, our timestamp-based concurrency control and even other concurrency control techniques say the later transaction is the one that should be aborted. The one that started first, okay, should succeed because that started modifying the data first. If something else came along and started overwriting its data, that's the second transaction problem. So let's abort the second one. Okay? So now we need a way to figure out if there are 2 transactions that are causing a conflict, okay, then which one is the later transaction and which was the earlier transaction. Okay? So that's what we need to do. The way we are going to essentially do this is we are going to put logical timestamps on transactions. Okay? This could have been a physical timestamp as well. You could have actually put a clock value and say this transaction started at noon and that one started at 12:05. So that's a later transaction. That's if there's a conflict, that's what I bought. But you don't need to use real timestamps. You can do the same thing with logical timestamp because that also gives us the happened before relationship. Right? So that's what we will do. Every transaction is going to be given a timestamp. Okay? If transaction I wants to do an operation that conflicts with transaction J, you are going to essentially say which of these 2. So now there is a conflict. So which of these should I abort? You compare the timestamps, okay? And you do want the timestamps to be comparable. Okay? Remember that in Lamport's clock, you got a partial order, but we said there are ways to make it a total order. So assume that they are comparable, and then you essentially kill the one with the later timestamp. Okay? And the way you are actually now going to keep track of whether there is a conflict and on whatnot is for every item in your database. Okay? Let's say there are items A, B, C, and so on. For every item, you are going to keep two timestamps. Okay, you are going to essentially say what is the maximum read timestamp and what's the maximum write timestamp. It's like saying what is the timestamp of the most recent transaction that read this data item, and what is the timestamp of the most recent transaction that wrote to it. Okay? Just as your file modification time and file read time, saying when was the file last modified, when was it read, you do the same thing for each data item. When was it last modified? In this case, you'll use a transaction timestamp, and when was it last read? So you have these two values that you keep track. Okay? And now we'll see how to figure out if there is a conflict. So if you want to perform a read on X, some transaction wants to perform a read on X, you check the transaction timestamp and you compare to the write timestamp. Okay? If there's a later transaction that has already modified it, that's a problem because that's going to cause a conflict. Okay? Then you are going to abort it. Okay? Otherwise, you'll let the read proceed. Okay? And then you also update if the read is successful. You're going to update the read timestamp saying here's a more recent transaction. So this is the latest one that has read it. Okay? So you're going to do a max of the two and store it here. Okay? And then when you do a write, you're going to check, is there a more recent transaction that has either read or modified it? Okay, so if you do that, that's again either a read-write conflict or a write-write conflict. In either of these cases, this write should not be allowed to succeed. So you are going to abort it as well. Okay, and otherwise you're going to perform the write and you update the write timestamp. Okay, so essentially you're using the notion of timestamps to figure out if there is a conflict or not for each data item. Okay? And if there is a conflict, you're going to abort it. Otherwise, you let it succeed. And then you keep track of the most recent read and the most recent write of a transaction to each data item. Okay? Yes, your question. Yes, the question is when you undo the transaction, are you going to undo the changes? Yes, the abort of I doesn't mean that just this read is going to fail. You have to go back into that undo log and change everything that the transaction has modified, not just say that this read cannot proceed, right? Because you have to go back to what was the case before the transaction. If it's a private workspace, you just throw away the copy. Nothing has to change. But if it's the log concept, then the transaction has actually made changes to the actual database. So you have to go back and undo, sort of play the undo log and revert back to the old state. Okay. Yes. Okay, that's a good question. The question is that how do you check the atomicity of whatever is happening, where maybe you check and you say it's okay, but then before you perform read, something else can happen. So you're absolutely right. You have to do that, but then we assume that you grabbed a lock on that read. So while you're doing that, nothing else can actually perform a write operation, right? So while this operation is happening because there's a lock on that object, that cannot occur because all of this is inside the operation after you get the lock. Okay, very good point. Because if there was no lock here, this is not running atomically. You could make this check saying everything is good, something else runs, and then you are in trouble, right? So that you don't want to happen. So all of these have to execute atomically, which means that the lock manager will actually have to get the lock, so that you cannot have this problem. Okay, yes, question. Okay, question is when you do an abort operation, is it just killed or are you going to rerun the transaction? That's your question, right? Okay. So there are two ways to look at this. Okay. There are some transactional system where if you abort the transaction, the application code, meaning your code that you wrote, where you issued the query or the transaction, gets an error message. And then you have to use an exception handling saying, if transaction not successful, then you call it again. So in this case, a retry is done by the application. Okay, so that's the standard approach. Of course, you could have essentially have the transaction manager itself retry it for you. Saying if you abort it, let's say you retry it, and then you do that maybe some number of times, and hopefully it succeeds. Okay, so I think that typically database systems will allow the application to make a decision. Okay, because they can decide how to retry and so on and so on. But yes, If you want the transaction to succeed eventually, you have to restart it. Okay? Whether the application code restarts it or is done internally, that's an implementation detail. Okay. All right. So I think we are done here for today. I have 10 minutes. I am happy to take any questions about the midterm or anything else that you might have. You can ask it here. You can also come over if you want and we can talk. Okay. So let's stop here. And then also good luck with the exam. If you have questions, we are available tomorrow and Friday to answer any questions. Okay. I'm sorry. Okay, we'll fix that. We can ignore for now because yes, thank you. It's just showing the same thing in a picture.